Now some applications. The real pioneer of carbon-14 in the world of biogeochemistry has been Tim Eglinton, shown here, with his father. This is Jeff Eglinton, who was, as Kate mentioned, was my postdoctoral advisor at Bristol, England. Jeff was an organic chemist who got interested in the natural products distributed in rocks and everywhere else, and is absolutely the founding father of molecular organic geochemistry, an utterly brilliant man. If you were in his lab, he would drive you nuts. He came around all the time with an idea about what you had to do when you had just barely started what he'd talked to you about yesterday. And at first, it was nerve-wracking. But of course, it was also fantastically stimulating. A marvelous guy who was a huge innovator. I can't imagine how many people went through his labs, hundreds. And we all absolutely loved it once we sort of adjusted to it. Jeff died in February of this year. Very, very nice guy. He was working on a manuscript weeks before he passed away. A fabulously productive guy. And Tim, his son, is in his personality stunningly different, and in his ability marvelously equal. A terrific guy who opened the door of carbon-13. And I'll give you a couple of examples. One of Tim's first ideas was to straighten out problems with paleoclimatological indicators in marine sediments. Marine sediments are dated using foraminiferal microfossils, these little bits of calcium carbonate that get formed by eukaryotic carnivore way up at the top of the ocean that eats algal cells and stuff like that, and it produces a bit of calcite as a microscopic shell. And calcite is the densest sedimentary mineral in the ocean. These things drop like micro cannonballs right through the ocean, land in the sediment, and if you find a well-preserved foraminiferal microfossil with all of its details intact, you can be practically certain that it formed right above the spot where you found it, and it simply dropped in. So you measure the age of that microfossil, that bit of calcite, and it tells you the age of that horizon in the sediment. In the same sedimentary layers, you find organic particles. And we interpret them in terms of all kinds of other factors, including sea surface temperature, partial pressures of CO2. All those kinds of signals can be carried by the organic molecules. Now, the organic molecules don't have exactly the same physical properties as these microscopic cannonballs of calcite that drop in. So there were plenty of sedimentologists warning the paleoceanographers, look, there's differential bioturbation of these calcite particles on the one hand and the organic particles on the other. So you guys who are assuming that the calcite age and the organic particle age are the same, you're probably off by a few hundred years, because as there's bioturbation in the sediment, the organic stuff will be stirred downward a bit, and it'll have a different age, slightly different age, than the calcite microfossils. So the idea was to measure the carbon-14 in the organic material on the one hand, and the carbon-14 in the microfossils on the other, and find out just how big this correction should be. And Tim had, with one of his students, who I'll introduce a bit later, pioneered the analysis of carbon-14 in organic material to the point that he could do it at the level of specific compounds. So he could isolate using preparative capillary gas chromatography. Over a week of injections on a chromatograph, you could accumulate enough of a particular molecule to have enough to burn it, convert it to graphite, and measure the carbon-14. And so we expected to get differences the order of 500 years. And the site that was chosen, here's the cast of characters. Lloyd Keigwin is the paleoceanographer at Woods Hole. Now, Okouchi was a postdoc with Tim working on it, and I was just an analytical bystander. But Keigwin's favorite spot in the whole ocean is the Bermuda Rise, because you get a very rapid sedimentation rate, and as a result, you've got a meter of sediment corresponds to only like 10,000 years. So that you can measure time differences and variations very, very precisely in that high sedimentation rate. So the Bermuda Rise, a sediment drift, where stuff gets blown in and piles up quickly, was the site chosen. And here are the results. We had 3 different cores. And so G. ruber is a planktonic foram. Ages were measured. Here you see them. And here are the ages of the organic particles, where they were supposed to be a few hundred years older, maybe. They're thousands of years older. And the results are overwhelmingly uniform. I mean, there's no question. This is not a flake of a measurement. They're all just shockingly old in comparison to the sediment horizon in which they're found. The idea that this alkene, which is used as a measurement of sea surface temperature, or I should say also as a measurement of PCO2, that the one we find at 850 radiocarbon years horizon, it's actually pertains to like 6,000 years ago almost. And the fact that it's so much older tells us the equally grotesque truth that it must be a mixture of all kinds of stuff, and that it doesn't have the paleoclimatic or paleoceanographic meaning that we hope for. So the question is, well then, what's going on? And this is a nice demonstration of work with carbon-14. The first thing you do is you decide what's your best estimate of the real age of these sedimentary layers. So you make a graph of the actual calibrated ages from that program I was describing earlier, and you sort of smooth out the variations, and you come up with an age model for the core. So these are now our best estimates of the ages for each of these depth intervals. We claim we know these. We understand there are uncertainties. We even tabulate the uncertainties associated with those. I just haven't cluttered the graph or the table with them. So now you plot versus those calibrated ages, the ages of the alkenones, the ages of the total organic carbon, the ages of fine fraction inorganic carbon, which we went back and analyzed as an afterthought. This is calcite, just like the calcite that was used to establish the overall axis, but it's not intact, well-preserved foraminiferal microfossils. This is carbonate mud, ultra-fine fraction stuff. All of these fine materials, apparently, were just being blown around by sea currents on the seafloor, and blown around about equally. Not only are the alkenones and the total organic carbon old, the fine fraction inorganic carbon is old. There's not a big mystery here. It's just the small particles are being blown around on the seafloor and having this effect. Moreover, at least in the Holocene, the effect is biggest where the percentage of calcium carbonate is lowest. It's like silicious mud, silicate mud, that's being blown in apparently from the St. Lawrence fan that's causing the dilution of the carbonate and also importing the fine debris that's steering these ages to much older levels. Moreover, from this UK37 signal, which is a measurement of sea surface temperature, it even tells us that these things blew in from somewhere where there was cold water, which also fits with this happening, this stuff being imported from further north on the Atlantic seaboard of North America. Using these known radiocarbon ages and the known sedimentary horizon ages, we can calculate at the time this stuff blew in, what was its carbon-14 content then? And we do that in terms of delta 14C. If we back calculate from the age model the delta 14C of the forams themselves, we just reproduce that atmospheric signal that I showed you earlier. If we calculate it for the alkenones and the TOC, we get these numbers that are ridiculously different. Look in the Holocene. Here's a case in which the DIC, the dissolved inorganic carbon, was at minus 54 per mil. The alkenones were at minus 251 per mil. 200 per mil lighter. Here's another case in which they're almost 600 per mil lighter. The stuff that was being blown in varied. And you can make an interesting plot. Here's percentage of calcium carbonate, and here's the delta 14C value of the alkenones, the total organic carbon, or the fine fraction, relative to the delta 14C value of the forams in the same levels. So the difference, as I said, varies from about 600 per mil down to 200 per mil. And it co-varies with percent calcium carbonate, which is telling us that it's this mud, non-calcareous mud, that's dragging in this old stuff. And it's following this blue pathway from cold waters in the St. Lawrence fan region and dumping its stuff as it slows down here. Lower in the core, where the corrupting materials are warmer, it's apparently coming from these eddies on the western boundary undercurrent. There are two different kinds of diluent here. But the main problem is that we got a shocking but useful bit of information about sources of organic material and its ages in sediments from carbon-14.